Today we have Ramon Aguado. He came from Instituto de Ciencia Materiales de Madrid. He's expert on, well, many things, but especially on strongly covalent electrons and quantum transport, and these days on Majorana physics. So he's going to tell us about so you have written a very appealing title, I think.
Provocative title.
Provocative title. So,
okay. Thank you, Rosa. Yes, of course, let me thank Rosa for inviting me to give this talk. It's always a pleasure to come back here to this nice place, to Mallorca. So, as Rosa announced, I will be talking about Majorana fermions, and in particular the possibility of having Majorana bound states in solid-state devices, and I will discuss whether this exotic quasi-particle. So, as Rosa said, I'm working in Madrid at the Instituto de Ciencia Materiales in the theory department. So let me just start. This is of course the introduction. The first slide one has to put here is the starting point, is the Dirac equation, right? This is the Dirac equation for relativistic spin 1/2 particles. And the question that Majorana wanted to address is whether this Dirac equation for relativistic particles supports real solutions. This was the problem that Majorana wanted to solve. Real solutions of the Dirac equation. And in particular, what he found is that if you write down this kind of combination of Pauli matrices, these are these so-called Weil matrices in the Dirac equation, if you find this combination of Pauli matrices, which are entirely purely imaginary, then the wave function is indeed real. Okay? And this has very profound consequences, because if your wave function is real, it means that particles are equal to antiparticles. Of course, if a particle is equal to its own antiparticle, this can only happen if this particle is neutral. And then Majorana postulated that in terms of trying to demonstrate, to measure whether neutrinos are indeed this kind of Majorana particles. And there has been a lot of research, a lot of large experiments going on for decades, that so far there is no clear answer of whether these neutrinos are Majorana fermions. And this has also consequences in dark matter, supersymmetric. So, as I said, what Majorana found is that the wave function can be real. But actually, the most general formulation of this Majorana equation is this one, in which what you demand is that charge conjugation, that if you apply charge conjugation, that the charge conjugate wave function should be equal to itself. This is the more general representation of a particle being equal to its own antiparticle. And this, as you will see, has a very important meaning in the solid-state proposals. So if you actually write down the charge conjugation operator, just by linear spinors, you have some mass term. If you take this Dirac equation and explicitly apply this charge conjugation symmetry here, this is just this matrix operation, you end up with this equation here, which explicitly mixes particles and antiparticles. So you see that through this mass term in the equation, particles and antiparticles are the same, essentially. So this is an important result. Charge conjugation is the more fundamental symmetry you have to fulfill to have Majorana fermions. This implies that this mass term mixes particles and antiparticles, so at the end of the day, the wave function is only one. And this is this paper by Jacques and Rossi from '81. What they found is that the Majorana equation in 2 dimensions has 0 modes, has non-propagating solutions, provided that this mass in the equation has some vortex profile, some inhomogeneity. So this is a second important concept, is Dirac equation in 2 dimensions, provided that you have some kind of inhomogeneity in the mass or some kind of vortex generally, you find 0 modes. You have bound states of Majorana character. And this is about these solutions, exotic solutions of the Majorana equation. So these two concepts, charge conjugation and 0 modes in the Dirac equation, will be very important in solid state proposals. So let me just jump to condensed matter. There have been a lot of proposals on how to obtain this kind of Majorana modes in different condensed matter settings or solid state devices. The common ingredient is that all proposals are based on hybrid systems in which there is some form of superconductivity involved. And you will see why these excitations in a superconductor, if you take the VCS ground state, you have the superconducting ground state, Cooper pairs. If you study excitations on top of this ground state, these are the so-called Bogoliubov quasi-particles, which are explicitly combinations of electrons and holes. Okay? So by construction, and this is the so-called Bogoliubov de Gennes Hamiltonian that gives you these excitations in the superconductor. By construction, this Bogoliubov de Gennes Hamiltonian has electron-hole symmetry built in. Okay? So this is again the electron part, this is the hole part, and this is the pair in general are in states inside the gap of the superconductor. As I said, there is by construction a particle-hole symmetry in the solution, so it means that for any creation of a quasi-particle at a given energy, there is the same annihilation of a quasi-particle at negative energy. And these two processes describe the same quasi-particle. This is very important, because as I said, these excitations are combinations of electrons and holes. So the key idea of using these Bogoliubov quasi-particles to create Majoranas is to create a 0 mode. If you create a 0 energy excitation in one of these Bogoliubov fully symmetric electron-hole combination on top of the superconductor, this is by construction a Majorana operator, and this is true provided that spin degeneracy is removed. Okay? Because if I have a spin, if I take into account a spin degree of freedom in my quasi-particle, this symmetry, this particle-hole symmetry implies that for a given excitation at positive energy and a spin up, say, you would have the equivalent excitation but at the spin down. So you still have a flavor, a degeneracy, which gives you a standard Fermi. So you need to get rid of a spin in order to have a non-degenerate 0 mode. This I said already, we need to get rid of a spin to have quasi-particle excitations in a superconductor, which are Majorana Fermis. This actually was very well known in condensed matter, and there are proposals already in the year 2000, even there are early proposals already suggesting that excitations in spinless superconductors, like P-wave superconductors, can have this Majorana character. There are many papers studying this in the early 2000 years, but these are kind of exotic proposals, you know, because P-wave superconductors in nature are very difficult. They are essentially exotic proposals, which were kind of interesting from the theory point of view, but of the fractional quantum Hall effect is really very difficult. So it was considered just, you know, like some exotic solutions in theory papers. So the real breakthrough came from this paper, this Fu and Kane paper, this is a PRL from 2008, in which they proposed to use a special combination of materials, a topological insulator, combined with S-wave superconductor. All the previous proposals were with P-wave superconductors, which, as I said, are kind of exotic. Take a three-dimensional topological insulator. On the surface of this two-dimensional topological insulator, you have a two-dimensional Dirac electron gas. I guess most of you know. So you know, on top of this two-dimensional electron gas, Dirac electron gas, you put an S-wave superconductor, and now you create a vortex by putting some magnetic material or some magnetic field. You create a vortex inside the superconductor. What they found is that this vortex can bind zero levels. Essentially, the zero-point motion contribution from this potential well is zero. Okay? This is essentially the same physics behind the zero Landau level in graphene. Because you have an extra Berry phase in the system, you don't have a zero-point motion, and you can have a zero mode. So they postulated, they demonstrated that this two-dimensional Dirac equation in a topological. I told you this paper by Zaikif and Rossi in nuclear physics in 81, in which they demonstrated that in two dimensions, the Dirac equation has zero modes, provided that this mass term has a vortex profile, an inhomogeneous vortex profile. And you see, this is essentially the same. So what Fu and Kane did was essentially to use this idea in field theory to actually build a realistic proposal to construct a two-dimensional Dirac equation plus some mass term. This is the mass in the equation. This is the veiling term, which acts as a mass. They cite it, I don't know how, but it's not that obvious, the comparison, let's say. But they knew, of course, and they cited it properly, let's say. So this was with topological insulators. A second important step came very close in year 2010, when different groups, in particular the Sarmas group and also Jason Olizea, demonstrated that the same kind of ideas can be coupling behave at low energies as relativistic fermions, and hence, again, if you put an S-wave structure on top of the two-dimensional gas and you create some kind of ferromagnetic domain or some magnetic field, again, you can trap zero modes. Okay? So these ideas were already that people in the labs can try to realize. So an even simpler proposal was this nanowire proposal. In the nanowire proposal, you just take a one-dimensional system or quasi-one-dimensional system with strong Rashba spin-orbit coupling, like indium arsenide, indium antimonide, these kind of systems that experimentalists can grow in their labs. These systems are known to have a strong spin-orbit coupling. So the idea is that if you put a magnetic field, you can create this kind of Dirac-like helical quasi-particles, helical particles. The idea is very simple. If you now put a finite spin-orbit coupling, you split these two bands. Spin-orbit coupling essentially couples momentum and spin, this Rashba spin-orbit coupling. So you remove the degeneracy between blue and green bands, spin up or down in some particular projection. Still near zero momentum, these two bands are degenerate. But if you now put a finite magnetic field which is perpendicular to the spin-orbit axis, you open a gap here. So now you have two completely independent bands. You have this blue band, this green band, and here these two bands are helical. So spin and momentum, for positive momentum you have, say, up spin in some axis projection, whereas for this green band, for positive momentum you have down spin. So you have helical channels. If one electron is moving forward, you would have spin up, pure spin up, whereas if it goes backwards, it's a spin down. So it's a pure helical system. Pretty much the same as the quantum spin Hall channels in a two-dimensional topological insulator. So this is the first ingredient, helical bands coming from spin-orbit coupling. Second ingredient, as I said, is to put some S-wave superconductor This is just a standard BCS Hamiltonian written in terms of spin, standard spin basis, which is this helical basis, these plus and minus bands. You end up, this is a trivial exercise, you end up with 3 different kinds of superconducting pairings in the system. So you can have 2 kinds of interband pairing, plus plus and minus minus, coming from superconducting pairing of these 2 bands, and still you have some remanent interband coupling coming from this term. The trick now is to put the chemical potential to the lowest band of the semiconductor. So you can essentially remove this band from the problem and you end up with only this kind of pairing, which you can write explicitly that this is an effective p-wave pairing. Okay? So this is how you create p-wave pairing out of s-wave pairing using Rashbach helical bands. Okay? It's clear so far, more or less, the idea? Helical means p-wave if you put s-wave superconductors. Okay, so as I said, it was known from the early to essentially one of these Kitai's model for one-dimensional p-wave superconductivity. Okay? And the idea is that if this system becomes helical, which in the presence of superconductivity means that this system is topologically non-trivial, you have at the ends of the wire 2 zero modes, 2 bound states here and here, which are Majorana fermions. Actually, to be true fermions. But the point is that essentially what you have created, as I said in the beginning, you have a superconductor. You have created a quasi-particle excitation in this superconductor. And because it's helical, you have created a non-degenerate excitation. So you have created a quasi-particle excitation which is split non-locally in the 2 ends of the nanowire. So these 2 Majorana excitations make a single fermion. So you have to think about this as, and this works for, ideally for an infinite nanowire. You split this fermion purely non-locally, and this is why these states are very robust for topological quantum computing, for instance. Because they are immune to local effects, essentially. Because this degree of freedom is non-locally stored. This is the idea behind this topological computation.
May I interrupt?
Sure.
I'm confused by the non-degeneracy you are emphasizing.
Yes.
Edges.
No, because here, when you are in this condition, when you only have one single band, you have single band superconductor. You only have one band and 1 degree of freedom, which is you have still some possibility of pairing between these points and these points because you have still some degree of canting coming from spin-orbit coupling. If this was a pure, spin polarized band, you cannot do a wave pairing, right? With a spin polarized band, but still you have a small degree.
That would be, let's say, a semi-infinite system, no?
Right.
So you are really considering the state on one edge.
No, both edges.
Both.
Yes, both edges make a single fermion. This is here. So you have one Majorana here, one Majorana here. Suppose they overlap, and there is a prefactor here which is non-zero, which is not written here, but suppose there is a prefactor here, and this overlap is non-zero. You would create a fermion state, but it's a single fermion state, it's non-degenerate. I mean, if it is still a trivial fermion, the idea is that you split a single fermion in 2 Majorana sectors which are completely delocalized. And actually, you see here in this slide, if you have the possibility of this pairing in the green band, for instance, then you have 2 possible bands, and then you have some kind of complicated pairing, but still you have an even number of bands in pairing. So an even number of fermions cannot give you a Majorana. So essentially, you pair fermions until you end up with a single excitation or not. If you end up with a single excitation, you have a non-trivial system.
But I think that what he means is that you can always construct any linear combination of this gamma 1 and gamma 2. And this is also a solution of the Hamiltonian.
Yes, but still you only have 1 degree of freedom.
Okay, that I agree, but people normally mention that Majorana Majoranas come in pairs.
Yes, this is the pairs. These are the pairs, 1 and 2. You have one fermion and 2 pairs, 1 and 2. Yes, so this is. And now you can.
Okay, but maybe later.
But I mean, if you have an even number, of bands, the superconductor is trivial, right? You need an odd number of bands.
Right, but the zero solution, I thought they were always coming in pairs.
No. You only have one single zero mode solution. Yes, if you have two, you cannot have 2 zero modes. If you have 2 zero modes, it's down, positive and negative energy. If they are at 0, they have to be, still you need a spin degeneracy if you have 2, right? If you remove the spin degeneracy, then you can have only 1. But I mean, if you have 2 Andreev bound states, I mean in general, or 2 Bogoliubov de Gennes quasi-particle, still with a spin degeneracy, you can approach 0, you know, arbitrarily close to 0, and they are trivial Andreev bound states, or trivial Bogoliubov de Gennes. If you still have a spin degeneracy, this is a trivial Bogoliubov de Gennes solution. This is why you need to remove spin degeneracy from the problem. Yeah, we can discuss later. Okay, so as I said, what you create is from spin orbit coupling, you create two helical bands, plus and minus. If you put some induced pairing at 0 magnetic field, this would be the Bogoliubov de Gennes picture. This is the electron part, this is the hole part. The idea is now, if you put a finite magnetic field, you open gaps in everywhere. And as I said, you have 3 difference of the magnetic field. You have the Fermi wave, Fermi momentum pairing delta plus here, and you may have some interband pairing. But the idea, this B critical, is written in terms of this parameter, which is the induced superconducting pairing and the chemical potential. The idea is that when B equals B critical, this gap, this delta minus here, closes here, and you actually end up with a Dirac-like Hamiltonian. So you have a Dirac-like Hamiltonian at low momentum with some finite momentum pairing in the system. Critical field, you have a trivial superconductor. When you reach this critical field, you close this gap and you have a Dirac system, and then if you increase magnetic field again, you open again a gap, and this is now a spectral gap, this is just magnetic field, and now you have created a topological superconductors with Majorana bound states. So the recipe is take one of these semiconducting system, put some magnetic field, hopefully you will be able to close this gap and create this topological regime in which you have these 0 modes.
But you need to close the gap at the 0 momentum.
Yes, you need to close the gap at 0 momentum, which is the one giving you this relativistic behavior. If my criterion for the gap is positive here, what I do is go from positive to 0 to negative. I haven't changed the bands, okay? And this is the vortex profile that I needed in 2 dimensions, which in 1 dimension is just a domain wall in the mass, okay? I have created a domain wall in the mass, which is the gap, and I have created, so it's always the same idea. I need to create some inhomogeneity in the mass, and then I have non-trivial topology in this Dirac system.
And you create this with magnetic field.
Yes. So you create this domain wall, this inhomogeneity with magnetic field. Correct. Okay, so this I said already, this is very attractive proposal because all the ingredients are available in the labs. You have nanowires with a strong spin orbit coupling, indium arsenide, indium antimonide with very strong spin orbit, large G factors. You want a large G factor because you want to induce a large can give you large Zeeman effect, okay? Still, you need to apply large magnetic fields, so you need superconductors with large critical fields. These are available, such as niobium or vanadium, and it turns out that these superconductors have very good proximity effect with these kind of semiconducting systems. There have many experiments in the published experiments. There have been many papers in the past demonstrating good proximity effect between indium arsenide and these kind of systems. And also in principle, these systems are gate tunable, so you can move this chemical potential and you can reach this helical condition. So the simple idea would be, as I said, just put a normal contact here and just study transport. So if you study transport for increasing magnetic fields, at some point you will reach this topological transition. You have these zero modes, and the presence of this zero mode in the superconductor will give you perfect Andreev transmission. So it will give you a peak of conductance, of unitary conductance 2e squared over h. In magnetic fields, what you expect is to have a gap closing. As I said, you need to close the gap, and then at some point you have a zero bias peak, which signals the presence of this Majorana zero mode in the system. So this is what experimentalists try to find. And in 2 years there was Majorana madness. I mean, a lot of papers. This was in March, actually in March 2012. Leo Carbonodians, everybody knew kind of in advance, so everybody was expecting the announcement. So he announced the measurement of Majorana fermions for the first time. As I said, the particle physics community was not successful in measuring Majoranas. So he announced the first signatures of these Majorana fermions in nanowire devices. They published their paper 1 month later in April, and there were a lot of news and views and physics viewpoints and so on. So right after the Delft experiment, a few labs in the world repeated the same zero bias peaks at signatures of Majorana fermions. So you see essentially same title everywhere, sometimes anomalous, but always zero bias and Majoranas and these kind of things. Okay, so let me explain very quickly the Delft experiment. As I said, this is an image of the real sample. You have an indium antimonide nanowire. You have a superconducting contact here, niobium. You have some normal metal here. You put a magnetic field parallel to the nanowire for different increasing magnetic fields, and this is the induced gap in the nanowire, and you see how for increasing magnetic fields, at some point you see this zero bias peak emerging. And this was understood as a strong signature of Majorana fermions. I mean, they did all kinds of sanity checks to really check whether this is a true Majorana fermion or not, zero bias peak, gate dependence, magnetic field dependence, proximity gap. This is 250 microvolts. The critical field that you expect is around 0.1 Tesla or so. And this is pretty much the region in which you start to see the zero bias peak. So, we were all very happy. It seemed that the experimental conditions, this is the angle rotation. When you rotate the angle, the peak disappears. So it was kind of robust. So there were a few things that were not really understood. For instance, I told you that you need to close a gap in order to have a topological system, but here you don't really see a closing of the gap. You see a peak over h, and this is 2 orders of magnitude less. But all these, let's say all these details can be understood if you do a kind of realistic calculation. The single band nanowire is too simplistic. If you study a multi-band nanowire and you take into account the smoothness of the confining potential and so on, you can understand things like the non-closing of the gap. So we did some calculations in this paper, and for instance, this is a theoretical plot, and you see how you see this emerging zero bias, which is the topmost, always the topmost subband, the first that becomes topological, but still you have the contribution from the outer, from lowest bands, and these bands, if the chemical potential is here, these bands here, the Fermi momentum of this band is way much larger than the Fermi momentum here. So essentially all the signal from this band comes from the trivial. So you don't really see the closing of the gap coming from this band. So you see the gap from the other experiments kind of confirming the Delft data. This is Weizmann Institute, this is the Monty-Heibels group, in which they see some emerging peak as a function of magnetic field, and actually they kind of see the closing of the gap, and this is actually how they reported their data. They say that this is the closing of the gap, and this zero bias peak is a Majorana fermion in their system. And there are also some experiments. Aaron Fink in Urbana, they also study a similar system. They see also these zero bias peaks. Also Charlie Marcus in Copenhagen and Harvard, they also see this kind of zero bias peak. So you know there is evidence. There is this kind of strong evidence from Delft. There is subsequent experiments from other labs in the world that seem to give kind of systematic behavior. Systematic behavior meaning information. There were many theoretical works. There are other scenarios that can give you essentially the same phenomenology that cannot be completely ruled out. In particular, disorder and weak anti-localization can give you similar peaks. Disorder in particular is very important. Also 0.7 anomalies and Kondo physics, which are essentially the same kind of physics, can give you this kind of zero bias peaks coming from Kondo physics. And also actually some non-trivial behavior of Andreev states that I will explain can give you also this kind of physics. So all these effects can be classified, and the second group is whether quantum dot physics, you know, Kondo physics, Andreev states, and so on, are related to quantum dot formation. So whether quantum dot physics is relevant at all in this Majorana nanowires. So I will focus on this second question. So for this, I will use our recent paper. This is an experimental paper from Silvano Franceschi's group in Grenoble. I did some theory for them. And this is essentially the same, similar system. This is an indium arsenide nanowire. This is a superconducting contact. This is vanadium. And this is again a normal probe, which is weakly coupled to the nanowire. The charging energies of this nanowire are not negligible. You know, are 3 to 10 times the induced gap, which in this case is 500 microvolts. So at least you have to think about of charging effects as a possible source of non-trivial effects in your system. So the minimal model that can give you the physics of charging effects is assuming that this is a quantum dot here, is an Anderson model coupled to some superconducting VCS system. So this is standard parameters for Anderson model. In particular, this is the Hubbard U, the charging energy. This is the coupling slides. This is the impurity, Anderson impurity. This is the coupling. And this is the superconductor. This is all standard. Well, you can write Green's functions for this problem and extract, let's say, experimental quantities out of these Green's functions. I mean, I'm not going to tell you about technical details. If you want technical details, I can discuss with you afterwards. The only thing I want to say is that in the large gap limit, if you assume that the gap is the largest scale in the problem, you end up with a self-energy which is static. The frequency dependence goes out of the problem. This is static self-energy, and this off-diagonal term you can actually write as an effective pair in the Hamiltonian. So this is now a kind of trivial Hamiltonian because you can actually diagonalize this problem, okay? You can't understand from this talk. If you understand this, I'm happy. So you have a superconductor coupled to an Anderson impurity, okay? And there is some limit in which you can diagonalize the problem, and you will see that in general this is also true. And you can have two different sectors, two different ground states in the problem. You can have a doublet sector in which you have spins up or down, and a single spin up or down. So this is an odd fermion, an odd fermionic parity, odd ground state. But you can also have a VCS singlet sector, which is a linear combination of doubly occupied sites and empty sites. And this is an even parity, fermionic parity, okay? And this is the phase that is very simple. You have two competing scales in the problem. For large U, for large charging energy, the system wants to have single fermions, right? Wants to avoid doubly occupancy, because charging energy is very large. So large U wants to have an odd fermionic parity in the problem. Large coupling to the superconductor wants to have even parity because it wants to have VCS ground state, Cooper pairs in the system. So Cooper pair pairing competes with charging energy, okay? So large coupling to the superconductor always give me a similar electron hole symmetry, can give me a doublet phase, a doublet ground state with odd fermionic parity. Despite uncoupling my system to a superconductor, the system prefers to stay in an odd fermion number, okay? And this line separating this dome this DOM from this blue region is the line separating the singlets from the doublets. So if I'm able to cross this line by changing parameters in the problem, I do a quantum phase transition. I change the parity of my ground state. Okay? This was for large gap. If I now put a finite gap, I still have quasi-particles between the impurity and the superconductor above the gap. So I may have also Kondo physics going on. So large coupling can give me singlets that can be of VCS type or Kondo type, whereas small coupling or large U can give me doublets. Singlets and doublets, okay? This is the only thing you have to remember. So this is at particle hole symmetry, and this is the phase this is the same line but going in this direction. This is the line separating singlets and doublets. And actually this plot was done by Johnson here. Superconductor. And this is reflected in the appearance of subgap states. So changes in the ground state parity appear as subgap levels crossing the Fermi energy. So as I said at the beginning, you have excitations, Bogoliubov-de Gennes excitations in the superconductor at finite energy. If this excitation crosses zero energy and becomes negative, it means that this is actually my ground state now, right? And the VCS is now the excited state, right? So even a classical impurity, a classical spin can lower the energy of the system and create parity crossings. This is well known since the 60s. And these are the famous papers by Liu, 65, Shiba, 68, Rusinov, 69. This is why these Bogoliubov-de Gennes quasi-particles in this contest of spin impurities are called Yu-Shiba-Rusinov states, or these days, because we are very lazy, we just call them Shiba states. Okay? But Shiba states polarize Andreev levels, if you wish. So this is Yu-Shiba-Rusinov. Also Sakurai has a very important paper from 70 in which he explained how these level crossings explain this change in the ground state in the superconductor. Okay, so as I said, you can have these bound states inside the superconductor coming from a spin. And this was for a classical impurity. This paper is from the 60s. Now if you put a true quantum impurity, you have quantum fluctuations, and you have a bit more difficult problem. You have Kondo physics going on and so on. But the key idea is these Shiba states, okay? These parity crossings in a superconductor. So you have this phase diagram, and as I said, by changing parameters of the impurity, you can change the ground state of the singlet of the system. And actually, you can tune the coupling to the superconductor in this nanowire experiment by changing the gates. So this gamma S in our model can be tuned experimentally, let's say. So you now put a finite voltage across the system and you induce Andreev reflection processes. You inject an electron here, and this electron can be converted into a Cooper pair in the superconductor by reflecting as a whole. And this is conductance, the IDV, as a function of gate, which is essentially E0 in my model, and V, which is essentially energy. These lines are my Andreev bound states. So if this line is always positive, it means that my ground state is always a singlet, because I am always creating an excitation in the system. So I'm in this part of the model. Whereas, well, and this I have to say, and these kind of experiments have been done in many systems, like self-assembled quantum dots, carbon nanotubes. Rosa was involved and Johnson were involved in this PR, Andreev bound states. So this is for singlets. If you now lower the coupling to the superconductor and you are in this part of the phase diagram, you can actually cross this line. If you stay here, you move, and at some point you enter the doublet phase. And this you actually see, because this line, well, let's say here, this line crosses zero, and at some point you create a completely different system, which is this loop here, in which you have crossed zero energy. So you go from a singlet to a doublet. You keep changing the gate, and at some point you cross this zero energy again, so you have to understand this as the theory is correct. So by tuning the coupling to the superconductor of this nanowire, I change the ground state of my system. And this I prove by measuring these zero energy crossings, or these loops. But I'm going to demonstrate, or to try to convince you that this is actually true. And this is kind of the merit of this experiment. Okay, as I said, peaks in the IDB measure excitations in the superconductor. Okay? So if my ground state is a singlet, my excitation should be a doublet. Okay? I put an electron, a quasi-particle in my system. If my ground state is even, so if I put a finite magnetic field, my excitation is now split. I remove spin degeneracy, right? So from one doublet, I now have two spins. So I have two possible lines, two possible excitations in my system. You follow me? I was in a singlet ground state. I remove spin degeneracy. I have two possible excitations. So I have two possible lines in my spectrum. And this is what they measure. I told you that this is a singlet, an excitation out of a singlet. So this is a doublet excitation. If I put a magnetic field, the lines split everywhere. Okay? Now, suppose that I am in a doublet. If my ground state is a doublet, my excitation is a singlet. Okay? So if I put a magnetic field, if my ground state is a doublet, because my excitation is a singlet, has even parity. So if it is true that my doublet is the ground state, if I put a magnetic field, I should only see one line, because the excited state is a singlet. And this is beautifully seen in the experiment. So inside this loop, you only see one line. Outside the loop, you see two lines. So this is highly non-trivial. I mean, if you think about it, it's trivial, but experimentally it's non-trivial because the Zeeman splitting depends on gate voltage, right? Well, as you move in gate voltage space, you may see Zeeman here, but you may not see Zeeman there. And this is okay. So this is again the same idea as a function of magnetic field. If I am in a ground state which is a doublet, if I increase magnetic field, I only increase the distance between my states. But because my excited state is a singlet, these lines do not split. Okay? So this is this linear Zeeman dependence. But at some point you start to see this deviation from this linear behavior, here and here. And actually we understand this because this line, if you want to continue here, this line has a strong anti-crossing with the continuum. Remember that you have a lot of them make it go down, okay? And actually we did some analytics of this anti-crossing which agrees with the experiment. So we understand the anti-crossing. So this is for singlet. The point I want to stress here, if here, even though I have this strong anti-crossing, the lines never cross zero because I am in a singlet excited state. Now, if I am in a doublet excited state, I have additional negative energy here. Okay? So I should see four lines in the spectrum. But when these lines cross zero energy, I change the parity of my ground state. So if this line, when I increase magnetic field, at some point becomes a doublet here, once they cross the spectrum, they should become two lines. So this is a kind of a strong claim and a strong result. I start from four lines, and when they cross the Fermi energy, out of the blue, they become two lines. Because again, I have done a quantum phase transition in my ground state. And this is what is experimentally. Very nice. You have these four lines here, and when they cross zero, you no longer see them. That magnetic field induces a ground state parity transition, which you see as a zero bias crossing here. Okay? And this is a contour plot of the same result. These are the four lines. This is experimental contour plot. And because this anti-crossing that I told you, you see that this zero bias peak can survive up to pretty high magnetic fields. So this is around 1 Tesla and up to almost 2 Tesla, you see a zero bias peak. And this is just physics of Shiva states, okay? That we think we understand. This is just non-trivial Zeeman splitting of Shiva states in a superconductor, where they claim to have observed the gap closing and the zero bias peak coming from Majorana modes. And in my opinion, what they see is the same that we see here. This is just non-trivial, let's say, non-trivial physics coming from Coulomb blockade in this superconductor. Nothing to do with Majorana, or at least not a strong evidence of Majoranas, because we understand this in a kind of nice, I would say nicer, in simpler manner, okay?
What's the dimension of the dot in your experiment? And that's
essentially the same. That's a very good question. So typically, if you compare, and this is a very good question. So in our case, for instance, the distance between electrodes is around 200 nanometers. And in their case, it's 250 or so. I don't remember, but you know, same order of magnitude. And the key point is that you may have a long section of the nanowire covered by the superconductor, but if you have a normal electrode on the other side, and you somehow create a tunnel barrier to measure transport, you may create bound states in the scene, in this normal part. And these bound states, if you create a quantum dot, this bound state may have charging energy. So this physics is relevant. This is our claim.
In the Delft experiment is an order of magnitude larger.
The Delft experiment is larger.
Microns.
Yes. They still see so on. This doesn't work. So I will comment on this afterwards. Well, let me skip this. So this was just a Coulomb blockade physics. This is the physics of Shiva states in a superconductor. If you now put, as I said, if you now put Kondo physics, you can also have quantum fluctuations due to quasi-particle exchange. So you can have also singlets coming from Kondo. And this is another experiment from Silvano's group in Grenoble, in which I also participated, doing some theory. And here what they superconductors, this is superconductor, in this case this is aluminium, and this coupling between the systems are very asymmetric. So we can actually go from Shiva states when magnetic field is zero, the superconducting gap is well developed, although it's a soft gap. And we understand these negative differential resistance peaks as Shiva states. I can discuss with you afterwards if you want. I don't have time to discuss. But we have a full theory explaining these negative peaks as Shiva states. Peak. And we understand this emerging zero bias peak as coming from Kondo physics. Okay? Because in this case, the gap that we induced, that they induced, is a very soft gap. Instead of having the typical VCS density of states in which you have zero density of states inside the gap, it's not like a square. It's more like a U or something like this. And there is some finite density of state inside the gap near zero energy. And this is another thing that is very important, because in all these experiments, the gap is soft, Kondo peaks. This is our conclusion in this PRL. And this is actually a measurement of the soft gap. And you see the gap is always finite. The density of state is always finite inside the gap. This is the development of soft gap as you increase magnetic field. So once you have a soft gap, it's not that surprising that you have Kondo physics, right? Because you have quasi-particles inside the gap. So you always induce Kondo physics. So there is another cleaner samples. And then in their case, they have very hard gaps. This is aluminium, and they have very hard gaps. And they measure Andreev states. Again, you see these nice loops here. Again, doing transport. In this case, with a weak probe. And what they report is that when they increase magnetic field, they have these Andreev states, but at some point they have a zero bias origin. So in the conclusions of the paper, they say unexplained narrow zero bias feature. So, and the ratio between the coupling to the normal probe and the superconducting probe is like 0.1 or so. So they have a hard gap system with a zero bias anomaly, and they say that because this is a hard gap system, kind of conclude. But we have done a very recent collaboration with Rosa and Jonsu and Rock Fitco, in which we have actually studied very carefully the phase diagram of this normal quantum dot superconductor system for the first time. There was no previous studies of the exact phase diagram using numerical randomization group approach. And actually we have found that even a very weak coupling to this normal part, to this gamma n, in this case to this, which is, 1 order or 2 orders of magnitude smaller than the coupling to superconductor, can change this boundary between singlets and doublets. And actually in the doublet phase, if you study the density of a state, you have a very narrow Kondo peak coming from this weak coupling to the normal part. So again, doublets can give you Kondo peaks, and we believe these kind of needle features they find in their paper are coming from Kondo physics. Non-trivial Kondo system, because in this case it's a very weak Kondo system. But again, if you move along this phase to a doublet singlet transition in which you have another zero bias peak coming from this crossing to zero, and then you will see a splitting. So you can have zero bias peaks in the singlet phase, coming from the mechanism that I just explained, from these parity crossings coming from magnetic field. But you can also have zero bias peaks in the odd phase, in the doublet phase, coming from Kondo. So zero bias peaks are not really a measurement of, or are not conclusive states from a doublet to a Kondo, and you see this narrow peak, how it increases in size until you reach this dashed line, which is the singlet doublet transition. So suppose you have some finite temperature in the system, this narrow feature would be probably removed from the experiment. What you would see is at some point some emerging peak here that grows and then splits. Again, the same phenomenology of Majoranas, which does not depend on the parity of the ground state, which is very important. So this is the Majorana formulas, or Majorana bound states, to be rigorous. I have explained that how this non-trivial Zeeman splitting, these parity crossings, can give you non-trivial Zeeman splittings in the system that essentially mimics the physics of Majorana bound states. And actually, I would say that mimics is a weak word, because our understanding now is that actually these parity crossings are precursors somehow of Majorana physics. So it's not like you have two completely independent effects in the system going on. It's just that these parity crossings that may appear before the topological transition are give you essentially the same phenomenology, because they are actually the precursors of these Majoranas, okay? With the Shiva phenomenology that again can give you this kind of Majorana-like phenomenology without Majorana fermions. Kondo physics can be also of relevance, even in a quote-unquote tunnel configuration. So, the title of the talk, the provocative title, have Majorana bound states been measured? Maybe. I cannot say no, maybe. I have to say the Delft data seems very consistent. I've discussed this data with Leo, and he has given talks and so on. They have new experiments, very careful experiments, so everything seems quite consistent with this Majorana interpretation. This is Delft, but there are other experiments which kind of confirm this Majorana interpretation, which I have to say are less clear, are weaker in that sense. So they are not. Let me just advertise this paper that we just published in PRL. So our point of view now is that you have we need new experiments, and in particular junctions, Josephson junctions, can be very useful to study non-trivial topology. So we have to move from zero bias experiments and go to junctions. This is our view. So for instance, supercurrent in Josephson junctions can give you very nice features coming from non-trivial topology. Let me thank my friend, my experimental friend Silvano De Franceschi from Grenoble. Also Eduardo Lee is a very good postdoc in Grenoble. He did all the tough experiments. And these are the two experiments I've been discussing. These are the Andreev levels, and this is the Kondo experiment. And also my theory co-workers, Pablo San Jose and Elsa from postdocs in Madrid, in CSIC, in our institute. Elsa is now at the Autónoma University. This is my student Jorge Luis for this last paper, which is very nice, together with our friend Jonsu here, and also Rock Fitko, who did very nice and very tough numerical randomization group calculations. And with this I finish, and I thank you for your attention.
So thank you very much for this nice talk. So, well, maybe there are some questions. Yes, please.
If I understand well, the only effect, or when you say this other scenario, this alternative scenario would be irrelevant or not necessary.
Right. Yeah, it's a very good question. So RASBA.
What would happen if you add RASBA?
RASBA helps. So if you don't take into account, I mean, this was the explanation in terms of just an Anderson model with a charging energy and coupling to a superconductor. And then you have the physics of parity crossings, okay? So you have these parity crossings, and this is without any RASBA spin orbit. Now, if you put RASBA spin orbit, what you have is every time you have crossings, you open minigas system, for instance, all these crossings coming from Zeeman. If you put RASBA, it helps, because essentially all these crossings become anti-crossings, and all the states near zero become flat, even flatter. And this is the thing I told you over lunch yesterday. Even without interactions, if you study the physics of these Zeeman crossings, if you now put RASBA, you open mini-gaps, and now these states become even flatter. So it helps.
And
in short.
That in the case that RASBA dominates, if not
of Kramer's pairs of RASBA type with Coulomb bouquet, which will give you the same phenomenology. Instead of a spin Zeeman, I would have Kramer's pairs, right? But it's still the physics of odd parity versus even parity would be the same. So when I say spin, you would say Kramer's doublet. You see? That is the same. And this we know from previous papers, for instance, also with Rosa and Jonsu, we did the Josephson effect with the spin orbit coupling, in which all the phenomenology that you expect from a Josephson junction with the spin, you recover it with the spin orbit coupling, and you have a pi junction behavior coming from a spin orbit. It's the same.
I think we can maybe stop and continue the discussion with Ramon.
Okay.
So let us thank again.
Thank you.